And next presenters are Team 4. Team 4. Welcome. And you are going to... Go ahead. Okay, give them a hand, please, Team 4. And you guys have 45 minutes.
Good afternoon. I'm Che, and we are Team 4. I'm really excited to be here to finally reveal our writing product, Purium Plus. But we wouldn't be here without months of intense work and passion from our team. So I'd like to introduce members of the schools committed to this project. Led by Hongik University, 5 schools are joining with us on stage. We've been working in groups of customer insight, industrial design, engineering, and manufacturing. And for the past 9 months, we've been communicating through emails and conferences. And on May, we held a workshop with the global students joined together in Seoul. This was our last year concept, Purium. The name of Purium comes from a German word meaning seniors having pure passion in their heart. However, we noticed there is a problem in its driving and mechanism. So we decided to set a different folding type for Purium Plus, an upgraded version, and it was the best and accurate choice we could make with the decision matrix. For today's presentation, you'll be followed by our team. Starting from Customer Insight, please welcome Kyungmin Kim to the stage.
Hello, my name is Kyungmin Kim, and I'll be speaking on behalf of Customer Insights team. So, to begin with, our project goal was to design a personal mobility for seniors traveling first and last mile distance. So during our second year, we're to start from the beginning. We're to set up a study plan of where it's going to be used, who it's for, and how it's going to be used. Our answers to where, who, what, and how will carry through further on our research and insight. So, where will our product be used? Let's look into environment and condition. Our target country was based on the number of senior populations, purchasing power, and traffic environment. Considering all these aspects, we found that China was our potential country. Since China is well known for having a large number of daily cycle users and a bike sharing system. However, traffic environment is very dangerous in China, and people are easily exposed to danger. To find who will be using our product, we began our research. So during the last 6 months, we went out on field and we met seniors and experts from China, Korea, and the US. The 6 methods we've done for research was brainstorming, online survey, field research, interview, immersion, and usability test. First, we conducted research we can do on desk, which was brainstorming and online survey, which wasn't enough, so we went out on the field and met seniors. We asked questions on their personal lifestyles and their personalities. Next slide, please. Through our interview, we realized that these seniors have in common. They were passionate and outgoing, was always challenging and starting something new. We call them active seniors. Next slide, yeah. To look more closely into their lifestyles, we follow them into buses and subways. We took notes and captured what they see, think, do, and feel while taking the public transportation. In subways, many looked exhausted and busy, and they checked time in every minute. Next, we brainstormed in order to find our users' needs. Their personal need in life were to be independent, keeping a healthy lifestyle, and spending time productively. During traveling, they didn't want to be in danger, or carry heavy loads, or waste time. Therefore, we provide these functions and systems to our mobility: tilting system, ultrasonic sensor, pixie sensor, storage, and application. Now I would like to introduce our personal mobility. In the market, there are many different kinds of riding. However, they're either too dangerous or designed for much higher age. So our product will be in between, providing a safe but enjoyable riding. It will be designed for seniors traveling first and last mile distance. It should be a safe and portable personal mobility. We would now like to finally introduce our Purion Plus. It is a simple folding, safe balancing, and smart sensoring product. To see how our product will be used, we would like to introduce Wang Xiaobang, an active senior using Purion Plus. He's currently retired from work, and he studies in senior college. He rides Purion Plus because he doesn't want to waste time waiting for the bus. He begins his day by dropping his grandchild to school and rides Purion Plus to college. Now we would like to introduce his journey starting from his house. He sets his Purion Plus to Pixie mode to drop his grandchild to school. Then he turns on his Purion Plus application to receive directions and signals to his destination. He also checks his bus schedule not to be late. He goes on and off the bus and rides Purion Plus to college. We would now like to introduce a short clip of his journey. Thank you. And our continuing presenter. Thank you. And our continuing presenter will be Han from Industrial Design Team.
Hi, this is Han from the Industrial Design Team. We will start the presentation with a trailer video of Purion Plus. So before we start writing the contents, I would like to introduce what kind of personal mobility we have tried to design. The target mobility should include these 3 points. For active seniors in China, used in a first and last mile condition as in personal mobility. The following presentation will be about how industrial design team met these points in the actual design. The concept of Purion Plus was all based on the active seniors in China. The research with the customer insight team has revealed that the activeness of seniors are pretty much restrained and that they prefer something classic, not too iconic. They still have the desire to look cool and young. The previous page, please. They still have the desire to look cool and young or the pure passion that Purion reflects, but at the same time, it should be safe. So by making a positioning map for styling, we have concluded that as the design form gets closer to the classic, the vehicle becomes stable than the iconic. This indicates that the styling strategy of industrial design team has to focus on restraining the form than before. Therefore, we have derived the keywords as pure, but firm, and moderate active. These are the inspiration images that we have done. We have felt that the martial art movements in the Chinese active seniors are pretty much similar to what they do. The packaging idea was derived from the existing core values of Purion. We have developed and specified the core values into these 3 keywords. With the typo structure, the mobility is stable than any other PM. It is foldable and towable, and it's also compact, but it hasn't lost its functionality. Additionally, by lowering the edge point by 135 millimeters, we have made writing in Purion Plus stable than before. So this is the final design we've proposed. This is a side view 2D rendering of Purion Plus. And these are the core reviews. We worked on this 3D modeling with the help of Alias. And this is how Purion Plus is used in the first and last mile condition. We will now watch a video of how Purion Plus is composed. Purion Plus is compact but functional. Its frames folds into half, and the cowl wraps its frames. It has a cargo on its right side. According to research by the customer insight team, it has been revealed that the customers usually felt the necessity of a cargo. When folded, the users can tow the mobility with the towing handle. The ergonomically designed towing handle makes the mobility portable. Purion Plus is not just a mobility, it's a mobility for seniors. Therefore, in the instrument panel and the saddle where the users directly meet with the vehicle, it should be ergonomically designed. In a busy traffic situation, users with degrading senses will feel that relying only on sight for acquiring the driving information, such as the navigation information, is pretty difficult and dangerous. Users will have to continuously look up and down, see the direction. Video, please. Therefore, with the collaboration with the customer insight team, we have added a haptic function. Users will be able to look front while still acquiring the direction information through the vibration alarm coming from the handle part. As the bone and the muscles weakens due to aging, the saddle had to be designed in a special way for the safe comfort of the users. Generally used saddles usually presses the hip bones of the users as seen in the images and causes pain. Slick shape is not what users can use comfortably. Therefore, we have designed a no-nose saddle type. It's wider but doesn't have a nose, and it gives comfort to the rider while riding. So this is it for the design descriptions, and we'll watch a final video of how Purion Plus works and runs. Thank you for listening, and please welcome Ashley from the product engineering team.
So good afternoon, this is Ashley Cho presenting on behalf of Product Engineering of PACE Team 4. For the past few months, we have been collaborating as a team to enhance the specifications of Purion to Purion Plus in the aspect of engineering. And today, we would like to share what we have been working on with all of you. The contents are as follows. So first, the ergonomics. In the process of designing Purion Plus, the first thing that we have considered was setting the H point and finding an appropriate writing posture for the users to feel comfortable. Therefore, we have decided to do a mounting test on active sinews using mock-up made based on the design dimensions. Video, please. The first mounting test was done by Northwestern University with the initial settle height of 700 millimeters. However, all of the participants felt the difficulties to mount onto the vehicle, and therefore we've decided to do another mounting test with the modified dimensions of 560 millimeters. The results were satisfying as all of the participants were able to mount onto the vehicle without the need to raise their legs above their waist. Now that the settle height was confirmed, we have then finalized the riding posture of the users as shown in the presentation. At last, with the human model size based on the market target, comfort assessment was done to recheck the comfort of the suggested riding posture. Next, the propulsion system. These are the selected motor and the battery. With the maximum power output of 800 watts and maximum torque of 25 Newton meter, its ability to accelerate vehicle was measured to be 1.89 meter per second square, which requires only about 3 seconds to accelerate the vehicle to its maximum speed of 20 kilometers per hour. The following products have successfully satisfied the given requirements, and they have been tested several times through sets of vehicle performance analysis. So the first thing that we have done was to calculate the demanding power of the selected motor to climb an inclined hill. With the maximum power output of 800 watts, Purion Plus could climb hills inclined by 5.14 degrees at a speed of 16 kilometers per hour. This is very important because what it implies is that Purion Plus has the ability to climb almost all the slopes in China with the selected motor. Also, to clarify whether our users will be able to drive Purion Plus for more than 50 kilometers after its full charge, we have calculated the capacity of the battery. Video, please. Assuming that Purion Plus is ridden on flat roads with the maximum speed of 20 kilometers per hour, we have calculated the battery capacity using a program called Electric Bike Simulator. And the results were amazing because Purion Plus could drive for 112 kilometers after its full charge. Additionally, with the use of a 14 amperes charger, Purion Plus only takes about an hour to be fully charged. Last of all, we've calculated the braking force needed to stop Purion Plus from moving, and it was calculated to be 745.6 Newton. The efficiency was found to be at its best when the braking force was distributed at a ratio of 1:2 to the front and rear part of the body frame. In such conditions, the braking time required to stop Purion was measured to be 1.41 seconds with a braking distance of 5.87 meter. So this is our final circuit diagram for our propulsion system. The next thing that I would like to talk about is the front suspension system. In an attempt to enhance the specifications, we have done a ride analysis and a handling analysis. To obtain an optimum value of our spring stiffness, we have done a ride analysis. And to confirm on the tread length of our Purion Plus, we have done a handling analysis. Both of the analysis was done by using MSE atoms with the input variables as listed in the table below. Video, please. In the given conditions, we have first done a ride analysis on a pocket road. As you can see in the video, we have modeled the roads given by using Siemens Annex and have done a simulation using MSE atoms. With the damping constant of such, the magnitude of the acceleration at the human center of gravity was measured to be at its lowest value when the spring stiffness was set to 250 pounds per inch. Similarly, another set of right analysis was done on slope roads with the equivalent spring stiffness of 250 pounds per inch. And in such conditions, the magnitude of the acceleration at the human center of gravity was measured to be 6,222.3 millimeter per second square. Moving on, to confirm the tread length of our Purion Plus in the concept of compact packaging, we have done a handling analysis. And for all three cases listed in the table below, we have calculated the critical velocity at the minimum radius of the test track. Taking the result of case 1 into further analysis, we have then calculated the time required to complete one single driving scenario that was given by PEMD road test. By using the tread length of 300 millimeters, approximately 10 minutes was required to finish a single driving scenario, which definitely satisfies the given lap time given by the PEMD road test. Last of all, we have done a rollover analysis to confirm and find an optimum tilting angle that ensures the stability of the drive. As you can see on the graph, the bigger the tilting angle, the faster the users could take a turn while maintaining the stability. And this is the final design of our front suspension system. Last of all, as our host has greatly explained in the very beginning of our presentation, Team 4 has addressed an issue of the initial folding mechanism of year 1, and therefore we decided to move forward with another folding mechanism. To do so, we have spent some time researching and studying the many different types of folding mechanisms, and we have classified them into groups of 4 according to their types. And out of the many, we have decided to move forward with the hot folding type. In the process of deciding on which folding mechanisms to go with, the things that we have considered most important was to make it user-friendly, easy, and intuitive. Also, by ensuring enough space for the tilting suspension to be installed at the front part of the body frame, we believe that we have enhanced the functionality of Purion Plus. Last but not least, the coexistence of cargo space with the compact folding has enlightened the portability of Purion Plus. And this is the 2 prototypes that we, Hongik University and Northwestern University, have managed to make. The one main significant difference between the 2 folding prototypes would be the way to activate the folding mechanism of the body frame. And this is the final body assembly of the folding type 1. Video, please. As you can see in the video, after the saddle frame and the footrest frame is folded in such directions, simply by opening the clamp at the bottom frame and pushing the rear frame forwards, the body frame of Purion Plus is folded compactly into half. We believe that this folding mechanism is intuitive, easy, and compact. Further explanations regarding folding type 2 will be presented by Jilin from Northwestern University. Please welcome.
Hello, this is Celine representing Northwestern University. The second design of the half-folding type relies solely on the bottom frame to be responsible for the mechanism, which means that it's also entirely responsible for the locking of the vehicle in riding mode. It is composed of 2 bottom frames for front and rear, a spring plate, sleeve, locking pin, and a cable. The cable originates at the handlebars, runs through the front frame, and attaches to the sleeve. The design utilizes cable activation to disengage a pin from the locking mechanism, which allows the bottom frames to rotate and fold upwards. As you can see in this video, the travel of the cable caused by the folding of the handlebars pulls on the sleeve that moves the pin along a slot and out of the lock. The lock is simply a hook that is prevented from rotating upwards when the pin is engaged, blocking its free movement. To relock, the handlebars are returned to their extended position, which loosens the cable and allows the pin to be returned to its locked position by way of a spring pushing on the sleeve. When you turn the handlebars, the cable is not pulled. But when you twist the handlebars like this, it is. Again, from the user's perspective, as seen in the animation, the user first folds the handlebars, which disengages the pin from the hook and allows the bottom beam to rotate. To change it back to riding mode, the user extends the vehicle and then extends the handlebars, allowing the hook and the pin to be engaged again. The rationale behind this design was that 1. It is the joint that withstands the fewest directly applied loads and moments. The lock is designed to withstand 100% of the externally applied forces with a safety factor of 2, the industry standard. And second, because our target audience is older adults, we avoided placing user touchpoints that required any uncomfortable movements, such as bending over or balancing on one foot. Handlebars are an easy location for the users to access, as it is the highest point of the vehicle, and it's also where the hands are naturally placed. Cable activation was the mechanism that allowed for the lock activation to be distant from the location of locking.
I'm very sorry for the inconvenience. We've also collaborated with Tuskegee University and regarding the structure analysis of the body frame. Hadia from Tuskegee will take over and present. Thank you. Video,
In an
please.
attempt to predict the performance of the design and to validify the safety of the design frame structure, we have conducted FEA analysis on the body frame. Considering that the materials used are both homogeneous and isotropic, we have done a linear static analysis on the body frame, as shown in the presentation, and have obtained results from the von Mises stress graph. For manufacturing, we have decided to use 3 different types of materials: aluminum 6061, aluminum 6063, and steel. The properties of the following materials are as stated in the table. We have distributed the total weight of a user of 95 kilograms in a ratio of 1:4 to the footrest and the saddle, respectively. By multiplying them with a safety factor of 3, we have applied the obtained load values of 2,234.4 newtons on the saddle and 558.6 newtons on the footrest. The loading conditions are indicated using red arrows in the presentation. To obtain a more accurate result, we have constrained the movement of the frames. First of all, to regions indicated using blue arrows, we have applied a pin constraint, limiting the freedom of any translational motion. Also, a simple support constraint was applied to the front and rear frame, which is required to support the model's load. Additionally to the constraints, we have also applied a surface-to-surface gluing contact condition to the meshes in the yellow regions to join dissimilar meshes and enhance the results of the analysis. This is the analysis result of the entire frame. The graph shows the maximum stress in each frame. For aluminum 6061, the maximum stress value of 79.6 megapascal occurred on the front frame. For aluminum 6063, the maximum of 134 megapascal occurred on the saddle frame, and for steel, the maximum of 342.2 megapascal was obtained in the sliding pin. However, since the yielding stress values of each material are higher than that of the obtained maximum stress values, no modification was required. As the analysis results suggest, we have concluded that no additional modification is needed in terms of improving the safety of the frame structure.
Thank you very much. Please welcome Wang Bo-fan from Jilin University.
This is Wang Bo-fan from Jilin University, and here is the thermal analysis of the battery set. In order to prevent battery degradation and to reduce the possibility of battery safety issues, we have conducted a thermal analysis on the battery set to check if it's generating heat within safe range during charge and discharge. We have assumed the cylindrical area as our calculation area in accordance to the layout of the battery on the vehicle. We have considered 2 cases of charging and discharging process. Considering that we have selected the general working condition of the battery pack on the e-bike, following are the factors that will affect the heat generated inside the battery. First, the current, the charging and discharging current. Second, the internal resistance of the batteries. And third, the room temperature. Values used in each criteria are as shown in the presentation. In order to successfully conduct the thermal analysis, ANSYS ICEM was used to measure the model as is shown in the picture. And we have also built two bodies to represent the air between the battery set and the box, and the wall of the cylindrical area and the box. And here are the results of the temperature distribution of the battery surface and inside the battery. As we can see, the temperature in the center part of the battery box is higher than that of the other part of the box. This is because it takes longer time for the heat generated inside the battery to transfer to the outside environment. And we can see that the maximum charging temperature is 312 Kelvin, which is 39 degrees Celsius. And this is lower than the BMS cutoff temperature, indicating that the battery can be charged safely. And here are the temperature distribution during the discharging process. And we can see that the maximum discharging temperature is a little bit higher, which was about 50 degrees Celsius, but it was still below the BMS cutoff temperature. The analysis results clearly show that the battery temperature range falls within the BMS operating range, verifying the safety of the battery. Thank you.
So hello again. This is the final vehicle technical specifications of our Purion Plus. As you can see in the presentation, we have managed to fold Purion Plus as compact as possible in the folded volume of 0.1 to 4 meter cube. The weight of the Purion Plus itself is 20 kilograms, with the wheelbase designed to be 770 millimeters. Regarding the propulsion system, the maximum speed of Purion Plus is 20 kilometers per hour, with its range after full charge measured to be 112 kilometers. The overall capacity that Purion Plus could endure is 136 kilograms, with the cargo space of 1.7 cubic centimeter. Sorry. To summarize, these are the three product concepts that we engineers try to pursue in the process of designing Purion Plus. As for simple folding, we have tried to look for a folding mechanism as intuitive and easy and user-friendly as possible. And as for safe balancing, we have employed a tadpole design with 3-wheel structure, making sure that users wouldn't have to hold on to the product after it is folded. And as for our last concept, Brawley from IPN will further explain. Thank you very much for listening. Thank you.
Hi, my name is Braulio and I'm a student from IPN. So I'm going to talk about the third key point, that is smart sensing. We achieve this with an ultrasonic sensor placed in the front of the vehicle. With this, we recollect information about the environment and we dodge obstacles. If there's any obstacle in the way of the user, the vehicle will stop. The video, please. We also made a following system that is going to be available at the online store. It will only work when the vehicle is in the carrying mode. Simply by wearing the color type we are going to provide the user, the vehicle will follow. So to do this, we have the Pixie Cam. The Pixie Cam detects color objects. So we measure an error between the center point of the camera and the position of the track object. With this, we move the servos in the camera to never lose track of the object. And with that angle, we move the way of the vehicle to follow the object. Because it's an autonomous system, we also need a way to avoid obstacles. So to go low consuming energy and low price, we decided to use infrared sensors and ultrasonic sensors instead of LiDAR. We have this in pairs to have redundancy on our system. We have one pair in the front, one pair facing left, and one pair facing right. So here's the overall block diagram of our system. We have the reference, that is the center point of our camera. We obtain data from the Pixie Cam and move the pan and tilting servos to never lose track of the object. We obtain data from the ultrasonic and infrared sensors to know where to move the steering servo and to turn on or turn off the brushless engine. So we wanted to be a modular system so every user can mount it by themselves. So we decided to go only with 2 modules. The first module is with the pixie cam and the servos to never lose track of the object. So we have our pixie cam, and as soon as detect the object, it's sure to turn on and follow the object, as you can see. Oh, sorry. The light is not helping, sorry. It is designed to be like in outer space or with low light, but not in front of the camera. So it detects the object, turns on, and follow. Okay? Our second module is the sensors module. The sensor module have, of course, the ultrasonic sensors, the infrared sensors. It also has the controller and the servo to drive the direction through gears. We made a small mock-up to test the behavior of the system. The video, please. Okay. We can see our object to track is the green ball. We can see even in the surroundings have green, the camera only follows the ball. And in the second video, you can see the collision avoidance systems. Before crashing, it goes backwards. So now please welcome John Wu from the manufacturing team. Thank you.
Hi, I'm Yanu, the presenter of manufacturing team. First, I'm going to address our business plan and affordability. Here are the main points that we are going to analyze. First is the analysis of our target market. China is the largest market of e-bike, which consumes more than 90% of world's e-bike. Furthermore, the e-bike with lithium-ion battery, like its Purion Plus, also accounts for 15% of the market. And as the leading market of China e-bike, the Chinese government is actively attracting the following companies to invest. The following is the market sales volume analysis. We predicted the sales volume of EPAC for seniors in 2030 under 3 factors. When it comes to the e-bike market situation, the mid to low-end market is already saturated with all sorts of Chinese products. So a differentiated strategy would be desired that carve out a niche market by targeting seniors with high-quality products. So we focus on stable and premium e-bike to gain a competitive edge. By considering the feasible market share, we decided to produce 135,000 units per year. Now, as for the analysis of plant location, Wuhan will give a presentation.
Hi, this is Xiang Zheng from Wuhan University of Technology, and I would like to give a brief description of how we choose the plant site. The site selection process is like this. First, we choose a country, and then compare the provinces in the selected country, and finally decide on the final city as the plant site. And in this process, we applied 4 critical judging criteria, which are land price, delivery expense, level of labor skills, and material accessibility. To choose the best international site, we evaluated 4 candidate countries: China, Korea, Vietnam, and Japan. And in this table, according to the 4 criteria, China is selected as the Purion Plus plant. And in the part of comparing China's domestic sites, we compared 4 candidate provinces and applied the same criteria. With relative data from National Bureau of Statistics, we concluded that Jiangsu province is the most appropriate place. So where's Jiangsu province? In the first map, you can see that Jiangsu is in the east coastline of China and quite close to Korea and Japan. Especially in Jiangsu, we choose Leiyungang, marking the second map as the final city. And here are the reasons. The first map shows the e-bike company distribution in China. And as we can see, the largest number of e-bike companies are located in Jiangsu province, which means we can easily find many highly skilled workers from similar factories. And the second map shows that Lianyungang, the city, is surrounded by a large area of source of raw materials, so its access to material is easy and cheap. As for the transportation perspectives, Lianyungang Harbor is one of the top 10 ports in China. So many possible ship routes facilitate the easy transport from the factory to the major ports in Asia and America. And as the starting point of China-EU Railway, the factories in Lianyungang can easily transport the goods through trains to the European metropolitans, including Hamburg and Madrid. Thank you, and now time back to Yunwen.
Okay, continuing with Juan's presentation, I will now discussing the analysis of Purine Plus. To estimate the sales price, we initially calculated the material cost based on the BOM. In the case of first-year Purine, it was $734. However, this year, there were some changes due to the increased cost of forging mechanism and the overall design specification. As a result, the material cost of Purine Plus has risen to $920. It is around 25% increase in the total material cost. In order to calculate and evaluate the sales price as efficiently as possible, we based the proportions on the US manufacturing cost structure. And by factoring the data provided by Wuhan, as well as our plant factors, we were able to make some adjustments. Through these adjustments, the sales price of Purine Plus is expected to be $2,330. The following is some financial analysis. We calculated a break-even point is 5.4 year, and the return on investment is 18.5%. Now, let's move on to our plant design. Our plant considers three factors, which are manufacturability, built-in safety, and the environment. First is design for the manufacturability. Our plant is based on smart factory. It features an open factory monitored and controlled from anywhere. Once the material is transferred to the production lines by AGV, the production line operates. And with IoT technology, the machines at each shop are connected to each other, eliminating wasted time and reducing in-process inventory. In addition, the integrated information system increases the productivity, enabling the closed-loop data sharing. Our production lines are as follows. The block structure used at body shop and paint shop improves space efficiency. And the U-structure process arrangement ensures the optimal use of our capacities. Next is an efficient manufacturing and assembly line. Our Purine Plus is based on modularity assembly, so we minimize the total number of parts assembled. Also, the efficient assembly sequence minimizes the assembly directions and handling. This is a process of Purine Plus. Video, please. Oh yeah. The bottom frame between them are assembled. The next procedure is the module assembly. The steering handle, the front suspension, and front wheels are assembled. On its backside, the saddle, the rear wheel are put in order. With the battery, the controller, and cowl inserted, the assembly is completed. Also, through sharing integrated product, process, and results information, all stages in their product lifecycle can share accurate information, not just isolated data of each stage. Second is design for the built-in safety. 60% of occupational diseases can be traced back to the musculoskeletal disorders. A combination of physical and psychological factors induces the disorders. So, from a physical standpoint, the chairless chair which supports the worker's lower body, the exovest which supports the upper body, and the automatic adjustable height control system can prevent the work-related injuries. And from a psychological standpoint, the working account system, health program, and eco-friendly workspace will provide a reduction of stress in the work environment. And the industrial safety applications provides guidelines for a variety of risks and sounds the alarm when workers go out of the safe zone. As a result, the workers can always be aware of their safety. Third is design for the environment. We will place the ion exchange scrubble next to the paint shop to realize the green production. It has high efficiency of removing more than 95% of harmful gases while eliminating the other emission and reducing water and power consumption by up to 99% and 75% respectively. And by considering the material of Purine Plus, we use ABS for the coal, which is an environmentally friendly material, and the recyclable aluminum for the entire frame. Also, our lithium-ion battery will be reusable. So we expect around 44% of the Purine Plus will be recyclable. And we will connect with ESS companies by using our business platform. Since China, the world's largest producer of renewable energy, is implementing the large scale of ESS projects and strong policy for photovoltaic power generation, there are clear advantages in achieving synergy through a combination of ESS and solar panel projects. And we estimated around 88,000 kilowatt per year can be generated by solar panels at Purine Plus factory. We will store this with purchased electricity in the ESS and use it efficiently. As a result, around 11% of the total power consumption to be replaced with renewable energy. By doing so, we can protect the environment in the production process. Now, this is the completed layout of our Purine Plus manufacturing process. I will show the visualization of this through Google Sketch. This is our Purine Plus. As you can see, our plant is U-structure process arrangement. When the production lines are activated by AGV, the processes of coal and frame are performed simultaneously at the body shop. After that, they go to the paint shop. Then the scrubble located outside sucks toxic substances coming out after the paint process. The frames and the remaining modules are assembled in the assembly shop. After the final test, they are packaged for distribution. So this is our overall plant process. I'd like to finish here by thanking you all for your attention. Thank you.
Thank you, Yeonyu, and thank you for all listening up to this moment. We've been working hard for past 9 months just to get what we have today. Please bring your hands together and please welcome Purine Plus.
Thank you. Let's give them a hand again. Good job, guys. Now we have a break, I believe. Where is Mario? We have a break, and we will finish the presentation after the break.